Okay, so now we're going to look at the Thevenin equivalent circuit for a particular problem. It says here, for the circuit shown below, what value of ZL causes it to absorb the most power? What is the maximum power that can be absorbed by ZL? Okay, so we've done this type of problem when they're resistors, and you know that the load resistance should be equal to the Thevenin, the load resistance should be equal to the Thevenin resistance, and it's quite similar here as we discussed in lecture. For us, if we're having a circuit with impedances, ZL needs to be Z Thevenin conjugate. And remember, if the reason this is happening is because Z Thevenin were written as R Thevenin plus J X Thevenin. If ZL were equal to RL plus J XL, you can see if XL equals minus X Thevenin, then those two imaginary terms cancel, and we're left with R Thevenin and RL, and we already know that RL needs to be R Thevenin, like is the case for everything purely real. So what that means is that ZL needs to be equal to Z Thevenin conjugate, because the real part of ZL is equal to R Thevenin. The imaginary part of ZL is equal to minus X Thevenin. So that's just the complex conjugate. Okay, so that means in this case, oftentimes we said we're going to, attach impedance between terminals A and B, and we want to know what that impedance had to be. Okay, well, if we want to do this, we can do it the same type of way that we did before. Let's say maybe the first thing I want to do is find V open circuit. So if I'm doing that, I need to set up my circuit. I'll have minus 30, angle 30 here. Here's 20. Here's J25 minus J10. And so if I open up where ZL is, I need to find V open circuit. And so, well, that's not actually all that hard. I can use voltage divider law. I have three impedances, but I can sort of easily do it. I need the V open circuit to be equal to minus 30, angle 30 degrees. So that's the total voltage, times the impedance that I want to know the voltage across, so that's minus J10, over minus J10 plus the other two impedances that I have there, so 20 plus J25. So I get minus 30, angle 30 degrees, times minus J10, so when I multiply that, I'll get 300J, angle 30, since the minus signs will cancel, I'll still be left with a J, and I'll have 30 times 10, so 300, over, in the bottom I'll have minus J10 plus J25 is going to be J15, and I'll have 20 for the real part there, and so that's VOC. Okay, the other thing that I'll need, and I really don't need that for the first question where it's asking what ZL needs to be. I could just come back here and say, oh, I'll do the sort of test source method, and the test source method would be coming here and taking this circuit and saying, okay, where I have that load resistance, I want to attach a source, which I'll call V-test, and I need to find the current coming out of it, which I'll call I-test. And that is essentially the same as finding the input resistance, or the input impedance, I guess we might say, looking back into the network that way. Now there's one other thing we have to do, and that is get rid of all of our independent sources that were in the circuit before. Leave all the dependents there. We have a voltage source here, so we need to get rid of that. And to get rid of that, we would short it out. And so now you can see, okay, here's one terminal and here's another terminal. The 20 plus J25 is in parallel with the minus J10, and that's what our input impedance would be, because you can see we can combine those 20 plus J25 in parallel with minus J10, and that would be just the resistance there by itself, and so V test over I test would be just that impedance. Okay, so we need to figure out what that is, and that is our Z Thevenin. And once we get that, we know that for maximum power transfer, we need to have ZL is equal to Z Thevenin conjugate. It's as simple as that. Now, what's that going to be? Well, let's get our calculator and figure it out. So for the 20 plus J25 in parallel with the minus J10, let's see, we'll get I get Z Thevenin is 3.2 minus J 12.4, and so that means ZL, which has to be Z Thevenin conjugate, is 3.2. Just change the imaginary part to the negative of the other one, so plus J 12.4. Okay, so it's as simple as that. And what that basically means is we can write, if we have our V open circuit, which I haven't calculated yet, let's say we calculate that, that will be $300J divided by 20 plus J15, and then I can multiply that by 1 angle 30, so I get here for this 1.435 plus J 11.91. Which, when I take the magnitude and phase, I could also have written it in this way. 12 angle 83.13 degrees. Okay, so now we have to do powers for the maximum power part. Let's just make sure we got the right answer so far. Notice it says ZL needs to be 3.2 plus J 12.4. Got it. Now we need to find the maximum power. Now, it's not saying these are in RMS, so I would suspect that that means it is in peak power, and so we need to use, since we are in peak form, we need to use 1/2 VI conjugate for the complex power. It specifically wants just to know the average power, and of course that makes sense because our equivalent circuit now looks like this. We have an equivalent circuit. If we put it, V Thevenin is equal to that V open circuit, which was 12 angle 83.13. And our Z Thevenin is 3.2 minus J 12.4. And there's our terminals A and B. And we're going to attach our complex conjugate for it. And this is important to realize. What happens again is the minus J 12.4 and the plus J 12.4 cancel, and now it looks like a completely resistive circuit. We have 83.13 degrees. We have basically 3.2, and we have another 3.2, and this is simple. We get half of the voltage here, half of the voltage there. We need to find our number, so we'll take 1/2 VI conjugate. It's going to be purely real in this case because this is 1/2 V. I is going to, I conjugate is going to be V over R conjugate. So we'll get 1/2 VV conjugate, that's the magnitude of V squared, over 3.2. Now what is this V that we've got right here across this 3.2? Well, it's half of the total voltage since both resistors are the same, so that gives us 6 angle 83.13 degrees. And so this answer is going to be 1/2. Magnitude of that is just 6 squared over 3.2. So when we work that out, we're going to get 6. We get 5.625 watts. Since that's purely real, we can just say it's watts. Okay, so the other thing I wanted to point out there is, remember, what would have been the formula that we used if these were in RMS values? We would have used S equals VI conjugate if everything was in RMS. It was in peak, so we had to use 1/2 VI conjugate. Okay. So now we're done with this particular problem.